Hello everyone, and welcome back again to another video on calculus. In this video, we will be covering the derivatives of exponential functions. So this is a long playlist of a long calculus playlist. We've done derivatives of products and quotients. Now we're moving on to exponential functions, and logarithmic ones will be next. So to start off, let us first remind ourselves of what exponential functions are. Exponential functions are just functions in which have the independent variable be in the exponent. So sometimes people say x must be in the exponent for it to be an exponential function. And yeah, this is generally true, given that it's a function of x. So x is the independent variable. More generally, it's just that the independent variable has to be in the exponent. Okay, so what is the derivative function of an exponential? Well, the rule says that if we have a function of the form a to the x, where a is a constant, like let's say 8 to the power of x, then if we were to take the derivative function f dashed would just be a to the x, so our original function, multiplied by this constant, the natural logarithm, or ln for short, of the base, which in our case is 8. So if we were to take the derivative of this, it would be 8 to the x times the ln of 8. Okay, and if we have a more complicated exponential function, for example 8 to the power of 5x plus 3, for example, we just apply the chain rule, and we set this to be the internal function, basically. So if we were to derive this, it would just be copying the original function first, multiplied by the ln of the base, so ln 8, and then also multiplying by the internal derivative of this function, which is 5. The derivative of 5x plus 3 is just 5. So that's our final answer for the derivative. Okay. Now here I have a special case. So f of x equals e to the x. So this is pretty much the same form as here. It's just that our constant a is the special constant e, which is approximately 2.7 or 2.8. Not sure. But anyways, this is a special exponential function, because if we were to differentiate it using this rule, it would be e to the x times the ln of the base, and the base is e, and the ln of e is just 1, and multiplying by 1 doesn't have an effect. So essentially the derivative of e to the x is just e to the x. So it's an interesting function which is its own derivative. And another example of a function which is its own derivative would be, for example, 3e to the x. If we were to take the derivative of this, it would still be 3e to the x, since we just have a constant multiplier. So let's move on to comprehension. We have to determine the derivative functions. So starting off with 5 to the power of x, I'm just going to say f dashed of x equals 5 to the x. First copy the function, and then just multiply by the ln of the base. So we're multiplying by the natural logarithm of 5, which is in simplest form. We can't simplify this any further. And if we had a complex function here that wasn't just x, we would still have to multiply by the internal derivative, the derivative of the function over here. But since we have just x, the derivative of x is just 1. So we're good. This is our final answer. Now next we have the function f of x equals 1 to the power of x. So I'm actually just going to rewrite this as 1, because 1 to any power is still going to be 1. So don't immediately just try to apply the exponential derivative rule on this function. Instead, realize that 1 to the power of x is always just going to be 1, and 1 is a constant. So the derivative f dash of x will be 0. Okay, 0. The next example is f of x equals 0 to the power of x. Okay, and again, we can simplify this function before actually differentiating. So I'm just going to rewrite this as 0. And note that this function is not defined for all x values. First of all, I'm going to write that f dashed of x is equal to 0. Since 0 is a constant, the derivative will be 0. And now we should probably still state the domain. So x has to be strictly more than 0. Okay, x can't be 0 because 0 to the power of 0 is not defined, and x cannot be negative because 0 to a negative number, for example minus 5, would be 1 over 0 to the power of 5, and 1 over 0 is not defined either. So x would have to be strictly positive. And the next function is e to the power of x. We already did this example, so we know that the derivative is e to the x. It's a function which is its own derivative. Okay, so the next function is f of x equals negative 2 to the power of x. And before thinking about taking a derivative or using an exponential rule, you have to realize that this function does not exist. Does not exist, okay? Because the base of an exponential function can't be negative, and it is negative in this case. So we can't speak of a derivative here, okay? Now the next one is f of x equals e to the x to the power of 5 times 3e squared. Okay, so 3e squared is, remember, just a constant. There are no x's in there. And so let's actually bring that to the front, this constant 3e squared. And then I'm going to use an exponent law to bring this 5 in here. So it's going to be e to the power of 5 times x. This is exponent laws. And so now if we were to take the derivative of this, we'd get f dashed of x equals to the constant 3e squared times e to the 5x times the internal derivative 5. The derivative of 5x is 5. And this is going to be 15e to the power of 5x plus 2. So I'm multiplying the 3 and the 5, and I'm using exponent laws since we have the same base over here. So I'm going to delete this and write it on top. So the derivative is 15e to the power of 5x plus 2. Okay, the next function is 7e to the power of x. Okay. So what we can do here is we have maybe one or two options. We also had one or two options for the previous one. We could have set this to be u potentially. Okay. Now for this one, what we can do is distribute this x to the e and to the 7. So I'm actually gonna write this down here. So 7e to the power of x equals to 7 to the power of x times e to the power of x. And there you go. You have a product of two functions, and they're fairly easy to differentiate, and then you can just use the product rule. Okay. Or you can say that 7e, okay, is just the base, and then you it's just a constant. So then you immediately apply the exponent rule. So it's going to be copying the function 7e to the power of x times the ln of the base, which is 7e. Okay, to get the derivative. So d over dx is going to be this. And now we can simplify this a bit. So 7e to the power of x times the ln of 7 plus the ln of e, using exponent laws, and I'll need brackets over here. So this is equal to 7e to the power of x times ln of e is just 1, so times ln of 7 plus 1. And that's our final answer. Cut. So f dashed of x is equal to this. And as you see, sometimes there are multiple ways of getting to the right answer. I'm not showing all the ways, I'm just showing one that works, the one that I think is the best. And in this case, got us to this answer, which is correct. 7e to the power of x times the ln of 7 plus 1 in brackets, like that. Now we have f of x equals pi to the power of minus 2x. Now pi, again, is just a constant, so it's another normal application of the exponent rule. So first step is to copy the function and then multiply by the ln of the base, which is pi, and multiply by the internal derivative of this function, which is minus 2. So in the end, the whole derivative is going to be f dashed of x equals to minus 2 ln of pi times pi to the power of minus 2x. Okay, there we go. Move this up here. And now, the next function is e to the power of g of x, where g of x is this polynomial over here. So the first thing I'm going to do is to write it out. So f of x is going to be, wait a minute. F of x is equal to e to the power of g of x. Actually, let's just keep it this way. Therefore, f dashed of x will be e to the power of g of x. First step is always to copy, times the ln of e times the internal derivative, which is g dashed of x. let's have it in this form. So e to the power of g of x, I'm just going to keep that way. I'm not going to write this entire polynomial in the exponent. And as for the ln of e, that's just 1. And g dashed of x will be 9x squared plus 4x plus 1. And what's the derivative of sine of 46 degrees? Well, it's independent of x, so this is just a constant, and the derivative of any constant is just 0. So we ignore it. And this is our final answer. E to the power of g of x, where g of x is just this polynomial, times 9x squared plus 4x plus 1 in brackets. Okay, that's it for today's video. I hope it was helpful. And in the next one, we'll be doing derivatives of logarithmic functions.